Hi guys, welcome to Nunley Math. I'm Aaron Nunley. Thank you so much for joining me for our lesson on the Pythagorean Theorem. We are working our way through a unit I call Geometry Basics. We already took a couple videos and talked about angles and angle relationships. We looked at what happens when parallel lines are crossed by a transversal and how that creates certain angle patterns. And we've talked quite a bit about both congruent figures and a bit about triangles, specifically the triangle inequality and how we can use congruence theorems to prove whether triangles are congruent or not, as well as to find missing angles in triangles. So we've done a lot with angles and triangles. This is our last lesson specific to triangles. After this lesson, we're going to move on to some other shapes, as well as moving on to our area, surface area, and volume formulas. So the Pythagorean theorem is our focus today, and we're going to go ahead and dive right in. The Pythagorean theorem says, in a right triangle, the measure of the hypotenuse is equal to the sum of the squares of the measures of the other two sides. Now, when most people read the Pythagorean theorem the first time, it's a little bit overwhelming because there's a lot of vocabulary in there that we have to make sure we understand. So just very, very quickly, let me make sure that we're all on the same page. The hypotenuse in a right triangle is the side that is across from the right angle. So since my right angle is right here, the hypotenuse is this side over here. Now, since the 90-degree angle is the largest angle in a right triangle, that also means that the hypotenuse is going to be the largest side. In our previous video about the triangle inequality, we talked about the fact that the larger this angle is, the larger the side across from it must be. The other two sides in a right triangle are referred to as legs. Notice that your two legs are the two sides that touch the right angle or that meet to form the right angle, and then their other endpoint is along the hypotenuse. It does not really matter which one you call leg A and leg B. That's purely arbitrary. It's simply meant to indicate that they are not the hypotenuse. So the hypotenuse is a term that refers to the side opposite the right angle. The leg refers to any of the other sides. So in fancy math symbolic writing, what we just said over here is written this way. C squared, or the hypotenuse squared, is equal to the first leg squared plus the second leg squared. Now, we are not going to develop this formula today. There are lots of other videos about where that come from. Our goal today is simply to be able to use this Pythagorean theorem to prove some things about some right triangles. I should point out that the Pythagorean theorem only applies to right triangles or triangles that have a right angle. If you are dealing with a triangle that does not have a right angle, nothing we say about the Pythagorean theorem applies, and you're going to have to find another method to find missing sides and angles in that triangle. So here's how we're going to use this. I might say to you, is this a right triangle? Or I might say, prove to me that this is a right triangle. Well, I have one side that measures 3 centimeters, one side that measures 4 centimeters, and one side that measures 5 centimeters. If this is indeed a right angle or a right triangle, the longest side is going to have to be the hypotenuse, which means I can take the Pythagorean theorem, a squared plus b squared equals c squared. And if this is actually a right triangle, when I plug these three values in, I should get a statement that is true. Or in other words, if I plug in 3 for one of my legs, 4 for the other leg, and 5 for the hypotenuse, then I should get a statement that is mathematically true. 3 squared, of course, equals 9, 4 squared equals 16, and 5 squared equals 25. And then 9 plus 16 is 25. We can prove using this Pythagorean theorem that this is in fact a right triangle. And since we know 5 is the longest side, we also can prove or have proven that the right angle is this one right here between the 3 and the 4. That's not bad, right? Tell you what, why don't you pause the video, try this one on your own, then restart the video to see if your answer matches mine. I'm going to assume you've already done that, and I'm going to go ahead and work this one out. I have an 8 centimeter side, a 14 centimeter side, and a 19 centimeter side. Since 19 is the longest side, if this is a right triangle, that means this has to be the right angle, which makes 8 and 14 my legs, 19 my hypotenuse. So I'm just going to take my formula, plug in my values, and then work it out. 8 squared is 64, 14 squared is 196, 19 squared is 361, and when I add 64 and 196 together, I get 260, which of course is not equal to 361. This is not a true statement. I guess I could even go through here and put a not equal to symbol there. That means no, this is not a right triangle. One more. Again, pausing the video, trying this on your own to see if it works out. I'm going to assume you've already done that. Since 13 is the longest side, that means if this is a right triangle, the 13 is the hypotenuse, and that must be a right angle. I rewrite my formula, substitute in the values that I think should work, 5 and 12 being the legs, and simplify to see if the sides match. In this case, they do, so yes, this is a right triangle. Now, I am going to pause here and just mention real quick, for my students, I always require them to rewrite formulas when they're doing a problem like this. There's several reasons for that. Number one, it helps us to organize our thoughts and keeps us from making careless mistakes. Number two, it helps us to memorize the formula. And number three, it allows other people to understand what it is we are doing, because this is a formula that is broadly or widely accepted throughout math. It's one that has been proven. Now, there is another thing that you can do with the Pythagorean theorem, and that is this. If we already know that something is a right triangle, and we know two of the sides of the triangle, but we don't know the third, we can use the Pythagorean theorem to figure out the measure of that third side as well. Because the Pythagorean theorem says if you square one leg, add it to the square of the other leg, it should equal the square of the hypotenuse. So since this is my right angle, I know that x is going to be my hypotenuse, and 14 and 10 are going to be my legs. So I'm just going to plug those in. It does not matter where the 10 and 14 go. Those could be switched as long as they're in the leg position. What is important is that the hypotenuse goes in position C. Notice I changed C to the letter they gave me. That takes it from the generic formula to something specific to this triangle. Once I know that, I do know that 10 squared is 100. I also know that 14 squared is 196. And I also know that 100 plus 196 is 296. That takes us down to this equation. 296 equals x squared. So the question becomes, how do I find out what number times itself equals 296? Or, since this number has been squared, how do I undo that squaring? Well, in earlier lessons, we talked about the property of equality, and we said something like this. If you have an equation like this, the property of equality says we can do whatever we want as long as we do it to both sides. In this case, I chose to subtract 7 from both sides because I know that 7 and negative 7 are additive inverses. They make a 0, and I know the identity property tells me that 0 doesn't do anything. The property of equality lets me do whatever I want to both sides, and I specifically picked inverses of one another. Likewise, if I had something like 3x equals 21, if I wanted to undo this, I would multiply both sides by 1/3, because 3 and 1/3 are inverses of one another, giving me 1x equals 7, or just x equals 7, because the identity property says multiplying by 1 doesn't do anything. And likewise, if I wanted to take 3x equals 21, instead of multiplying by its reciprocal or its multiplicative inverse, I could just use the inverse operation, which is division. In either case, to get rid of subtraction, or to get rid of addition, I subtracted. To get rid of subtraction, I would have added. To get rid of multiplication, I would divide. The same thing is true down here in this problem. If I want to undo squaring, I have to use the inverse or reverse operation of that. The inverse of squaring is taking the square root. So the property of equality says I can do whatever I want as long as I do it on both sides, so I take the square root of both sides of this equation. Squares and square roots undo each other, leaving me with just x is approximately equal to 17.2. Now, in an earlier number sense unit, we did talk about how we could use the Babylonian method to compute this by hand, but for this set of problems, my students are going to be doing this with a calculator. So I would just type in the square root of 296, and then I would round it off to the nearest 10th place. Now, this is not the time for us to focus necessarily on exponent rules, but I should also point out that this has another answer. X could be either 17.2 or it could also be negative 17.2 because negative 17.2 times itself would be a negative times a negative, which is a positive. For now, in this part of our unit, suffice it to say that that we're just going to use the positive answer because our distance or our length should be a positive number. So we're just recognizing that this is one of the two answers, but it is the one that is most appropriate for a distance problem, like the distance of this line. Want to try that again? Here we go. This is a right triangle. I can tell by the right angle symbol, which means the side across from that angle is my hypotenuse. So when I take my Pythagorean theorem, I'm going to plug in 9 as one of the legs and 9 as the other leg. I'm going to simplify those to 81 plus 81, and I'm going to add those together to get 162. Just like I did over here, in order to undo squaring, I'm going to square root both sides because I know squares and square roots undo each other, and then I'm going to type this into my calculator, the square root of 162, which is approximately 12.7 centimeters. Again, recognizing that negative 12.7 times itself is also 162, but realizing that we have to have a positive length for this side. Here's one more. Again, I'm going to recommend that you pause the video, try it on your own. I'm going to assume you've already done that, so I'm going to do this one a little faster. I plug in my legs. I square both of those. That's 121 plus 144. Then I add them together. To get rid of the square, I square root both sides. The square root of 265 is 16.3 or negative 16.3. But we're recognizing that we need to use the positive solution in this instance. That's not bad, right? Don't forget that you could have a triangle where they give you the hypotenuse and one of the legs is missing, but we're going to do that the exact same way. We're still going to take the Pythagorean theorem. We're still going to plug in the 8 as one of the legs, but this time x is also going to be a leg and 18 is the hypotenuse. Now, it doesn't matter where you put the 8 and the x. I make a habit of always putting my x first because to me, when I begin to simplify this by squaring, it looks a little more familiar to have a plus 64 instead of having the 64 on this side. I know to get rid of a plus 64 using the property of equality, I'm going to subtract that from both sides because a positive 64 minus a 64 gives me a plus 0, which I don't need to write down. And now it looks just like the problems on the other slide. How do we undo squaring? We square root both sides. Squares and square roots will undo each other, leaving me with 1x is approximately 16.1 meters when I do the square root of 260. Again, negative 16.1 would also make this true, but we would not have a negative side length. Last one of these, I'd recommend pausing the video, trying it on your own. I am going to do this one a little bit faster. Notice that we already know it's a right triangle. That makes the 38 the hypotenuse, which means the 38 is going to go in position C. X and 9 go in positions A and B. I like to keep my x's first. I'm going to square the 9 and square the 38. I'm then going to use the property of equality to get rid of the plus 81. And to undo a square, I'm going to square root. Squares and square roots undo each other. This is going to be about 15.6 meters. Remember, negative 15.6 also makes it true, but you want to have a positive length. Also keep in mind that this is the approximately symbol or about symbol. I did not mention that before, but it is something you are going to want to be aware of. Again, those are really the only two things that you can do, or the only two ways that these will look when you're trying to solve. Here again, these are the two things that could. So now you have three things that you can do with the Pythagorean theorem. Number one, if you know all three sides of the triangle, you can prove whether it's a right triangle or not. If you know two legs, you could solve to find the hypotenuse. And lastly, we just learned that if you know the hypotenuse in one leg, you can solve to find the other leg as well. Now, we can take these and put them into some application problems as well. These are going to be worked out the same way. You just have to learn how to recognize the triangles. For example, this says Mr. Nunley is on a nature hike. He hikes west for 4 miles. I want to go ahead and draw that as an arrow. I've got a starting point. Usually people look at west as being left on the map, so I drew my arrow that way. And then he turns due north and hikes for 2 more miles. It's getting dark. He wants to take the shortest route back to where he started. If that's my ending point, the shortest route would be a straight line. What is the direct distance back to his starting point? Notice, since I was going west and I turned to go north, that is a right angle or a 90-degree turn, which means I can find my distance using the Pythagorean theorem. I'm going to recommend you pause the video and try it on your own now that we've got the triangle set up. I'm going to do this one a little faster because right now the setup is our focus. To get rid of a square, we square root both sides. The square root of 20 is about 4.5 miles. Don't forget, when you're given a problem like this, it's often helpful to draw the picture, including some kind of labels and units. Once I see the picture, it becomes much, much easier because then I can recognize that this is a Pythagorean theorem problem. Last one, Mr. Nunley is helping to build a house for Habitat for Humanity. After an exterior wall is erected, he measures it to see if it is square. Square means, did my wall form a right angle or is it straight up and down? The height of the wall is 9 feet. He measures 12 feet across the floor from the corner and makes a mark. What should be the length of the diagonal from the top of the wall to his, oops, there's a little typo, mark if the wall is square? Now, this is actually how construction workers will check to make sure that they are building walls in right angles or straight up and down. They will measure out one direction, measure out another direction, and then use a tape measure to try and see if this third side makes this a right angle. If this is a right angle, that third side would have to be a squared plus b squared equals c squared. The third side would have to be 81 plus 144, or the third side would have to be the square root of 225, meaning that board length, or this distance from here to here, would have to be 15 feet. So as a construction worker, I would know that if I measure out 9 and I measure out 12, if this is a 15, then my building is straight up and down at a right angle. If this is not 15, it means my wall is crooked and I need to kind of flex it or bend it a certain way in order to make it fit. That's really all I have for you today. As I mentioned, the Pythagorean theorem is very, very useful. One of the most commonly recognized theorems in all of geometry. You are going to want to make sure that you commit it to memory. Thank you so much for taking the time to join us here today. I do wish you all the very, very best. If you wouldn't mind, please give me a big old thumbs up. And make sure you ring that bell to turn on your notifications. That will keep you in the loop about anything new that comes out from us here at Nunley Math. I wish you all the very, very best. Take care of yourselves. Bye-bye.